Now in this second lecture and all the ones following this morning, we will be using the same elements that we saw in the morning. So those basic the variables, the loops, the functions, and so on. But we're going to start extending, focusing mostly on using libraries with codes that already exist. So we saw some examples where we need to parse some files, or we need to do some processing, compute statistics, and so on. But there's a lot of those tools already pre-written in these libraries, and you have these libraries installed with Anaconda. So we're going to look at a few of them. First, we're going to look at this concept of namespace and the scope of the names, so that we understand what we need to do to use objects that are present in other modules and in other places in the library. And then we're going to see how we can import modules into our own code. And this will allow us to use code that was already written somewhere, either our own code or code from other libraries. And we're going to see now this afternoon how to plot data, how to create plots using the matplotlib library. So I'm going to show a simple example of plotting data, talk a bit more about testing our functions. So unit test means that we're going to test each unit of our program, each individual function, and we can create batches of tests so that when we have to change something or update our code, we can run all the tests again to make sure that everything is working fine. There are some sophisticated testing units in Python. We are not going to go into that. I'm just going to show a simple example, a simple way how you can automate the tests of your code. And then if you want to do something more sophisticated, you can carry on from there. And then I'm going to show a more realistic example at the end for creating an animated plot. So the idea here is, like I did in the morning, these more realistic examples are necessarily more complex because we need to deal with real data and process the files and so forth. So the idea is not that you can reproduce this without looking at the code or something like that, but you should be able to understand reading the code to figure out what it's doing. So that is the important first part, because memorizing the actual commands and things like that takes practice. You don't need to try to do that in one go. But if you understand how the code works, you should be able to read code and then adapt it to what you need. And if you can do that, then you can already do a lot of things, because it's easy to find online solutions for something similar to what you need, and then you adapt for your problem. So let's start with the idea of a namespace and the scope of the names that we use. So basically you can think of a namespace as a dictionary or a table that the interpreter keeps, where it associates each name to whatever it is that is stored there. So that table that tells it where things are in memory and what the names mean. And we have different namespaces because this way we can avoid collisions between names. We already saw that with functions, where each function has its own namespace, so it's okay if there is a variable inside the function that has the same name as a variable outside, because they live in different namespaces, they do not interfere with each other. So this way we can split our code into independent parts. There are different levels of the namespace. One of them, this built-in namespace, includes the basic keywords like for, if, things like that Python understands, and some basic functions. And this is always accessible. It's the basic type, the basic elements of the language. But then there are some cases. For example, we have here a string, this text A, B, C, D. We want to split this string using the split method. We already saw this. But if you simply write split with a comma, you will get this error, because the interpreter doesn't know what split is. Because there is no split function in this namespace. There is a split method that belongs to that string. So you need to specify that I want the split method from the string. And in that string there is a namespace for that object that has the method there. So this is the basic idea. Often you need to specify where the name belongs, so that the interpreter can find it. This is also an advantage because you could have a function called split and still be able to use the split method of the string, because there would be two different things, one outside, one inside the namespace for that string. The scope determines the yes. Mm-hmm. Yes. No, it's not. I'm referring to split that belongs to that object S. The output is returned from this function. So this is a function, it returns the output, but it doesn't change S. It just creates a list of fragments for S. It outputs on the console if you don't assign it to anything, because then in that case the console captures the result and shows it. But if you put a variable there equal to this, it will simply store in that variable. So there are different namespaces that the interpreter will look into when it tries to understand the name of some name that you give. And it will start with the local namespace, which is within the same object, method, function. So if you create here this variable, var2, it will assume it belongs to the local namespace here. So it will create a variable that is local to this function. If you ask for var2 in this case, since it exists inside the function, it will use that variable. If it doesn't find the name in the local namespace, it will look on the global namespace. There is this enclosed also, which we'll see this later in the last week, but it's basically when you create a function inside a function, it can access names from the outside function, the enclosure of the function. But we're not going to be using that now, so we can skip this step. And if the interpreter doesn't find the name in the local namespace, it will go up to the global namespace and try to find the name in the same module. So for example here, when print var1, there is no var1 inside this function, but there is a var1 in the module, and it will get it from there. However, if I create something here, var1 equals to some value, it will create a local variable because that takes precedence. So it will prefer to use the local namespace. Only if it cannot find the variable there will it look on the global namespace. And then finally you have the built-in namespace for things like print, def, and these basic keywords for Python. So pay attention, because you can create a variable called print, but if you do so, then you won't be able to use the function, because then it will not be able to see the function. It will use the variable because it has a higher precedence namespace. It's in the local namespace or in the global namespace of the module. So if we run this, this will print first I am global, which is var1. It's going to get from that one, but then it creates var2 and prints this one. And if we try to see what is stored in var2, there is an error. So var1 exists outside the function because it was defined in the global namespace. var2 does not exist outside the function, it was only created there inside. And if we create, for example, if we change the value of var1, this first print will have a different value because the function is looking outside for this variable since it cannot find it in the local namespace. But if we change var2, this makes no difference because this one is created locally and it's independent from the one outside. So remember that the interpreter will try to find the meaning of the name first on the local namespace, then go for the global namespace, which is the namespace for your file, for your module, and if it doesn't find there, it will try to find it in the built-in namespace where you have those basic functions like len and print and so on. So how can we now import something from outside our namespace into our namespace? Let's see, for example, so far we've been executing our modules in Spider with F5. We write everything, we run the code that is there in that file. But often we want to use code from somewhere else. So we need to import the names that we want to use into the namespace of our file, of our module. We can use this keyword, import, and give the name of a module to import into our own namespace. So each module in Python is a file with the source code, and includes all the objects that are declared there, like functions and so on. Everything that the file creates is included in the file. So let's say we have this quadratic module, which is where we implemented this morning the function to solve quadratic equations. And we could, if we are working in the same folder, or if this module is installed on the folders that Python knows about, so you have lots of libraries already installed there, we can just import the module using import and the name of the module. So in this case, what the interpreter will do is it will run this module and create all the objects the module creates. So for example, this function, solve quadratic. But everything belongs to the namespace of that module. However, we imported the name of the module into our own namespace, so now we can access everything that belongs to the module. For example, we can say that in the quadratic module, in this namespace, we find this function, and we can call this function. So we can call the function that we wrote on the other file by importing the other file. An alternative, if we don't want everything inside this file, we just want this function, for example, we can say that we can import the function from there. If we try to do it like this, we get an error because this name does not exist in our namespace. It only exists inside that module. But if we do it like this, from the name of the module, import what we want to import from there, the interpreter will run everything in the module, create everything in that namespace, but then we'll import into our own namespace whatever we specify from there. So it will create this function, and we will be able to access the function from our own module as if it existed here. So we are importing things into our own namespace. In this case, we can then use solve quadratic and get the result. So it was as if the function was created inside our namespace. We can also import something with an alias. So whether you do this from quadratic import the name as something or import as something, we can change the name. There are two uses for this. One, suppose we wanted to import solve quadratic from that module, but we already had something called solve quadratic here. So we could change the name, we could import solve quadratic with a different name in order to distinguish between the two. Or we want to use the module a lot of times, but we don't want to have to write the whole name of the module because it's very large, so we can assign it a nickname, something that is shorter to make it simpler to use in our code. This is especially the case with modules that are very used, such as NumPy for numerical processing or matplotlib for plotting and so on. They have some conventional nicknames that everyone uses for convenience. Okay, so let's see this in a particular example. For plotting, for graphs and bar charts and things like that, we're going to use this matplotlib library. This has lots of options, so if you want to do graphics a lot, you should take a look at the documentation and examples, because there are many things you can do here. We're only going to see a few examples, but you have a chapter on the book I recommend about this, and also the online documentation for matplotlib. There's a lot of code there and documentation for all the functions. If you just want to create one simple figure, then this is what you need to do. We're going to use the pyplot module. There are different variants for matplotlib, but I'm going to use this one. So we're going to import the pyplot module from the matplotlib library, and this is a common nickname for this plot. So instead of having to write this whole thing, we just call it plt, and then we use anything from there with the plt. So then we're going to use the plot function, and we specify this namespace, plt.plot, and the plot function draws a line graph with at least two arguments. First the x values, and then the y values, and then it shows the scatter graph. If you don't do anything else, in fact, if you just write these two commands, this will work on your on the IPython console, because this is a graphical console and it captures graphical objects and displays them, so these plots created. If you are not using this console, you will need to call the show function that will create a window and show the graph. So with Spider you don't need the show command, you'll see the graph immediately, but if you use some other, the basic Python console, you will need to call show. And this is what you can see, unless if you use IPython with that graphical console, you will see only the graph appearing in your console. If you are using Python outside from the command line or something like that, when you call show, it will a window will appear with your graph. So this is the basic plotting function. There are many others for bar charts and for things like that, but we're going to use this basic one to see an example where we're going to plot the tuberculosis infection loads in different countries using this data from the World Health Organization. So we have the data in a CSV file. This data has for each country and year there are estimates. These are indicators of the region, so on. We have the year here. This is the population estimates for the country, and then we have an interval for the average, lower bound, and upper bound for the infection rate in tuberculosis in that country. So we have a confidence interval there with a mean value and two bounds. And we need to load this and then gather the data for one country for all the years. So note that we have many different countries here in the file, and we also have for each country different years in the file. So we need to process the file to extract the information that we want. So we're going to load the CSV file. We did something similar to this by doing read lines and then splitting the data and processing each part individually. But it's often the case when you deal with some standard format, you won't have to do that. If you are working with some strange format like extracting data from an HTML file or something like that, you probably will need to split the lines and identify what you want. But if you have something that is standard like a CSV or an Excel file or something like that, then it's best to use a library that already implements parsing that file, and this makes it easier to extract the information. So we're going to use this CSV library. We can just import the CSV module, and it has a CSV reader function that takes in the object for the file, or anything that allows it to read the file. This could be something that is taking data from the internet or something like that, doesn't matter. And we'll process that file, parse that file, and return an iterator, something that can allow us to go line by line on the file. And we'll already identify what is string and what is number, split the different fields, and so forth. So what we are saying here is that we're going to process this file. This is the delimiter. You usually have to fill in some arguments. In general, these functions have lots of parameters, so many different options that you can fill in, but most of them you can leave in the default settings. If you want to change some of them, you can specify which ones you want to change and assign the value. Now, this is not something that we are supposed to memorize, but you can quickly look up online the documentation for the function or use help and figure out which field you need to fill in. So basically, this is where it will get the data, the file object. The delimiter is a comma here, the ones that separate the different values. The quote char indicates text. So these are strings that are not supposed to be converted to numbers. And we can also specify this quote non-numeric, which is an indication that the parser should interpret anything that cannot be converted to a number. It should interpret that as a string. Because sometimes you have text that is not within quotation marks, and then the parser will try to convert that to a number and give an error. So this is one useful way of just keeping that as a string if it cannot be converted to number. But you can see this in the documentation anyway. So when you try to read some of these files, just look up the parameters and experiment if you need. Now this will give an object that can iterate through the file. This is useful because sometimes we have a very large file and we don't want to put everything in memory at the same time. So if you have it like that, you can just loop through that iterator, and it will give you one line at a time. So all the cells in a list with the different values, but it will give you one line at a time. Or we can just use the list function that takes any iterator and builds the list with everything. So in this case, since the file is not very large, we do that and we read everything into memory, into a large list, and this function returns that list. So when we test the function, you see that this is a list of lists. Each of the individual lists corresponds to a line in our CSV file, and each line then is in order, in the same order that we found it there. So the first one is just a header for the column. It's all text, we don't care about that. The others are the data for the countries and the years. So we can, in this case, we are printing the first three elements of the table, so the first 3 lines. In this case, we are printing line 100 and the first 10 elements in this line, in this row. So we have these elements in this row here. And we can index a list of lists in this way by providing 2 different indexes, one for the row and one for the elements inside the row. It's this part here. So the CSV file is in the same folder. Okay? We have this function here that receives the name of the file, as we have the code, yes. And this function receives, or if it's in a different folder, we can just specify the path. It can be in a different folder if you specify the path. But in this case, it's called tbburdencountries.csv, and it's in the same folder. So when we give this name to the load data function, it will open the file for reading. So it obtains this object that allows the CSV parser to access the file, and then use this reader function from the CSV module that will read the files like we did before with the PDB files and things like that. But this function already knows how to process CSV files. So you just have to specify what is the delimiter, the quoting character for text. This is necessary so that when it finds something, in this case it's not a problem, but sometimes you can have text that has no quotation marks and then it will try to convert and give an error. So we specify these arguments here, and the reader will now be able to parse the CSV file and can read one line at a time and decompose it in the different cells of that row. So when we do this list, we create a list with everything that is extracted from the file. So this is basically how we get the CSV file into memory. We use that reader function there to do the parsing for us. And what it does is it gives us a list of strings with the data in the file, and a list of lists, with the data in the file, and each of these lists corresponds to a row. And it already does the conversion that we want. For example, these first cells are strings, but then these are the actual numbers that is already converted from the data. And now we have everything in the right format, and we don't need to write our own parser for a CSV file, which would be more work, especially if the CSV file has text that spans multiple lines and things like that. That can happen. So this can handle that data. Yes, in the lecture notes it's also explained that. But if you want to try, if you have your own CSV file, we can look at that and explain. Also, it's easy to find, if you look online on these libraries, it's easy to find examples for different files. So now we have the data in a list of lists, and it's all converted into numbers, the part that we want, the strings for the names of the countries and so on. And so now we want to extract from here the data corresponding to a specific country, because this CSV file has all the countries in the table, and we want to plot for a specific country, so we need to be able to identify the data that we want. So let's write this function. It receives this table, is the complete table extracted from the CSV file, and this code here is the three-letter code for the country. So each country has a three-letter code designating the country. We can use that to obtain the data for the country. And now it's simple. This is a list where we will put the data for that specific country. It starts empty. And now we go through all the rows in the table. So each row is a list of values corresponding to that row. And we are going to check if the element of index 2, which is the third element, this one here, corresponds to the code that we are specifying. So the third column in our table has the three-letter country code. So we're going to look at the third element of each row and check if it's the same as the code the function receives. And if it is, then we're going to put into this data a tuple with four values that we want: the year, the medium value for the infection load, the lower bound, and the upper bound, because these are where the columns are in that row. So this function extracts the data that we want for the country that we want. If we specify, for example, for Portugal, we get this data for Portugal, and here we are printing the first 5 entries. So these are the first 5 tuples with the year and the infection load that we extract. Okay, now we need to create a list of values for plotting on the chart. So we need the list of the years, a list of all the median, mean infection load, the lower bound for the infection load, and so forth. One easy way of doing this, we have so far we just extracted our data and we left it in the same shape, more or less. So each tuple corresponds to a different year. But now we want all the years in the row and all the values in the row so we can plot them. And this is something that can occurs frequently when we're solving real problems, which is sometimes the data is in some format that is practical for some things but not for others. But it's easy to create a function to change and not worry too much about that. So when you have that kind of problem, just think about how you can transform the data into whatever is convenient and then carry on from there. So this is what we'll do here. We'll generalize this. We have these lists of tuples with the data. But let's say we want a list with the values on the first element of each of the tuples, so we can extract the years. Or we can need the second element, so we extract these mean infection loads and so forth. So we generalize this. We can create a function that receives a table like that, so a list of tuples, and the index of the value that we want in each tuple. And now starts with an empty list and just appends that particular element of each tuple. So this D is each tuple in the data, each of these tuples of 4 values, and the D index is one specific value there. So we are taking that value and appending to this list. And now we can do this with the table for Portugal. We convert these tuples to a list using only the index 0, so the first one, and we get a list of all the years. Now we can do the same thing with the second one, and we use the same function for the different ones. So one thing that sometimes happens for when someone without programming experience does this is that you may think about doing one function for getting the years, one function for getting the mean load, and so on. But then you end up with 5 functions or 4 functions that are almost exactly the same. It's best to generalize from there, see what you can add to make it generic and work on any index, because then you only have one piece of code and if it has some error, you only need to fix it once, you only need to test it once, and so on. Okay, so avoid trying to duplicate your code or making very similar things when it's easy to combine them into a single one. Okay, so now we can plot the data for our country. Now, by the way, there is a slight detail here. Note that I'm using a list to store all these tuples, but inside each of them I'm not using a list but a tuple. I could use a list too. This could be a list of lists like the CSV reader produced, but usually if you have something for which the meaning is dependent on the position, it's best to use tuples because tuples cannot change. So it makes more sense to build it once and just keep it there. List you need whenever you have to append things. So if you have a set of elements, of objects that you need to keep adding to, then that has to be a list, because the tuple you cannot change it after you create it. There is one easier way of doing this with the zip function. So you may, if you look up things online in Python, you can often find this function, which basically takes in several arguments that are lists and then produces a list with by combining the first element of each of the lists, the second element of each of the lists, and so forth. So you could do these kinds of things using zip. And then another thing that you probably find sometimes online is this star before the argument. And what this does is it converts a list into a number of arguments. So if you have a list with 4 elements, if you put star before that, it will call the function as if all the elements were different arguments to the function. So there are some tricks that you could use to avoid doing something like this, but these require knowing a bit more about these details on Python. So this is just a warning that sometimes you can find these solutions. It's okay if you understand them, then that's even better, because you can write your code a lot more concisely and with less bother. But we are not going to focus on these details more of the Python dialect, but keep it more fundamental. So we're going to use the basic constructions of doing loops and conditions and so forth. So this would be the function to plot the country. We have the table with the data for all the countries extracted from the CSV file, the code for the country that we want to plot, and we're going to use that other function to get the data just for that country, then split it into different lists, one for the years, another for the mean infection load, the upper and the lower bound. Now we can create a figure. That figure function in plot will create a new chart. So if you plot several times, you are plotting always on the same chart, but if you call figure, you create a new one. So I'm calling figure here. I can even give the size. This is the size in inches, but the actual size, if you save it to a file, will depend on the dots per inch parameter, so for the resolution. But you can also use it for the aspect ratio, how wide and high it's going to be. So we create a new figure, and now we're going to plot the 3 series here. The x values are always the year. This is the mean infection load, the upper bound and the lower bound, and we can specify with a string some simple formatting options. This is similar to MATLAB if you use MATLAB. So basically, this K is for black, R for red, G for green, and the dash there is indicating that we want to draw a line joining the points. Now we can choose the title, and then if you are using the console, the IPython console, when the code finishes executing, the console shows you the graphs that you did not destroy, that are still in memory. If not, then you need to show to create the window there. So this would be the result here. We load the data from the CSV file, and then we get the country, the infection for that country, and we, in this case, we don't need this was the other test. We call plot country with the whole table and the country code, and it will extract that data and plot it like this. So now another thing that we need to do when we write a program with different functions, and that is a bit complex, we saw before, we decompose into simpler parts, and then we are putting the parts together to get everything working. So here we wrote several functions, and then we put everything together for the final program. But if we don't test each part individually, then we'll only notice the errors when we run everything together, and then it's harder to figure out what is going wrong, because it can be wrong anywhere in the program. So it's best to test each part individually before assembling or putting it together with the rest. And we can incorporate these tests into a module by taking advantage of this name property of each module. This is a special variable name that Python creates, and it's called underscore underscore name underscore underscore. And by convention in Python, these names that have underscores at the beginning and the end are special names. So you're not supposed to create your own like that. These are the kinds of names that Python uses for some particular end. And so each module has this name variable in its namespace. So it's 2 underscores name 2 underscores. It has to be written like that. And when you execute the module with F5, so if it's the main module for your program, this name has this string, main, 2 underscores, main, 2 underscores. This indicates that this is the module that is being run. Otherwise, if the module is imported from somewhere, then the name is the name of the module, the name of the file that's there. So, you can use this name variable to decide whether your module is being run or if it's being imported by something else. And if you write your function, let's say we have this tuberculosis program written as several functions in a module, which we can then import to plot something. If we do that, we can use a test to see if the module is being run or not, to run all our tests if we are running the module, if we press F5 on the module, but not run the tests when the module is being imported. And this means that if we are changing things in the module and want to test it, we are editing the module and we can just run it and run all the tests in one go. But if we are using the module, then we are importing it from somewhere else, and in that case, when it's imported, it will not run the test. It will just create a function and not keep testing itself, because that's not useful once we know that it's already running. So this is what we can do here. We can, at the end of this module, so after all these functions that we created, we can add this code, and we check if the name of the module, this underscore underscore name 2 underscore, is main, then we load data from this file that we assume is there when we are running the test. We print the values on the table, we get data for Portugal, and then we create the graph and so on. So all of these tests, we have them in the module. If we change anything, we can just run the module and see if everything is going okay by looking at the result of the test. However, since this is only run when the name is main, if we import functions from this module to somewhere else, the test will not run. So this part will not be executed. Okay? This is important because when we import a module, the interpreter needs to run everything in the module to create all the functions and all the objects that the module has. So if we don't have this check here, the test would be run every time we use the module somewhere else, and this is not very convenient, because then every time we would run some other program, we would get all these charts appearing and nobody would know why they are there. So this could be how we create our module for the tuberculosis plot. We have this at the end for the test, and also we can at the beginning add the documentation for the module. This works in the same way as for the function, but it belongs to the module, and you can also ask for help on the module name if you import the module, and this can explain how to use this module, which functions we could use, and give an example of how to use the module. For example, import from this module the load data and plot country, and then load some data and plot the country. This could be an explanation on how to use this module. So that if you import the module and ask for help, you get here a description of the module, so that documentation that you wrote. And now we can use this module in this way, from the module. So the tvplot is the file with all this code for plotting the tuberculosis load, including the test code here, because these are not run if we import the module, only if we run the module directly. So we can import from this module the functions that we need to load the data and plot the country, and then we can load data and plot the country and see the results. So now we have all these functions that plot the infection load, and we can use these from anywhere else in our code just by importing from there. Okay, so do you have questions about this so far? Yeah, this seems a bit confusing, but the important thing here is that when you look at code like this, you understand what it's doing. It's not important for you to memorize everything so that you're able to do this without looking anywhere. It's important that you start understanding what the code is, so that if you need to go back and look at it or modify it or something like that, then it's easier because you can figure out what is there. Okay? So this is not information for you to retain for the test, but it's a way for us to speed up the process, so that you can, even if you don't memorize all the details, at least you can work something out by looking at examples and so on, and build from there. So now let's complicate things a bit and see a more realistic example. This one for the tuberculosis is a very simple one, just have a TXT file and plot it. Let's do some animation. We have in here the Gapminder site. We have lots of good visualization there, but we have data for many indicators for many countries. So data comes in an Excel file with the country name in the first column, and then we have one column for each year and the values corresponding there. Note that there are some missing values, and so not all countries have values for all years. And we have one different file for each indicator. So in this case, we're going to use life expectancy, population, and gross domestic product per capita, and we're going to show how countries changed over the years on these indicators. And we're going to do something like this. So here we have China, Portugal, Spain, and Germany. We have gross domestic product here in a logarithmic scale, and here we have life expectancy, and we can see how over the years the countries move on this chart. The circles represent the population for the different countries. So this way we can represent these different data and show how the countries evolve over the years by animating the chart. So now this takes a bit more, this is a bit more realistic, but a bit more complex, because we don't have a single CSV file with all the data. We have many files, and they have holes because not all the data is available, and so on. So first we need to think about how we're going to store this data, because we have different indicators. For each indicator we have the country. For each country we have years, but we don't have all the years for all the countries, so we cannot do it in a simple table. And what we can do here is think of dictionaries. We can associate keys with values in a dictionary. So for one country, we can have a dictionary with all the values for all the years. So the year is the key and the corresponding value. And now, if we want to put all the countries in a dictionary, we have a dictionary of dictionaries, but that's not a problem. So we have this outside dictionary where the countries are the keys, And for each of these countries, we have an inner dictionary which has years and values. The reason for doing this is that the years are not the same for all countries, because some countries have missing values in the table. So this could be one way of processing this kind of data. We can read Excel using this Excel read library, and we also use matplotlib to do the plotting. So first we're going to create this function to read from an Excel file this dictionary of dictionaries with the data for all the countries for that indicator. So we're going to open this Excel book from the file, and we're going to get the first sheet here. So this, because these files only have one spreadsheet, so we're going to use always the first one. It's the only one there. So now this object, belongs to the Excel read library. You can look at the documentation that this one can read the Excel file, and then gives us this object that stores the spreadsheet for that page of the book. And now we can use this function, which tells us the cell value given the row and the column that we want. So we can go through the Excel sheets and get all the values that we want. So first we need to figure out for which years the indicator has values, because you see these are here, the years, and they are not always the same depending on the Excel file that we are looking at. So we need to read this row here and extract all the possible years we have. So basically we'll start with an empty list. We'll go from the column of index 1, which is the second column, up to the number of columns in this sheet. We are not looking at the first column because this is just its title, life expectancy or whatever. And then we are going to append here the value of these cells. So basically we are looking through all these cells and creating a list with all these years. This is necessary because different files have different years, so we need to know which years we have for that file. And now we're going to do the same thing over all the other rows. So starting from the second row, we're going to get the name of the country from the first column in that row. And now we're going to start the dictionary with the indicators for all the years. So we're going to look through, starting from the second column up to the end, and we check if there is something in the cell. So if the value of the cell is not an empty string, then there is something filled in. If it's an empty string, then it's these cells that don't have data, so we cannot use anything from there. So if it's not empty, we will get the year value from the list of years. We will use column -1 because the first year corresponds to the second column, the second year to the third column, and so forth. So we will fetch the year corresponding to this value and create an entry in this dictionary, year indicators, where this year is the key and the value is the value at that place in the spreadsheet. So basically we are checking to see whenever the cell is not empty, we add it to our dictionary, the year and the value for that entry. And now we can have this additional argument, additional parameter there, mean data, which is serves to filter out the countries that don't have enough points. So we can specify there a minimum number of years that we require for the country to be kept. Otherwise, we don't even keep data there. So this is just an example of what you can do to filter out data. So in this case, if the length of this dictionary year indicator, that is the number of entries there, is at least equal to minimum data, then we add this country to that dictionary, to the main dictionary there. So this will have an entry for which the key is the name of the country and the value is this dictionary with all the year values for that country. But if the country does not have enough data, we don't add it, so we don't keep that information. Now we can test this. We import from this module function. So you can do it like this, or you can run the module, but this is just to illustrate the importing method. Then we load this indicator here. This live X variable is now a dictionary with the entries for all the countries. And so we can look at the entry for Portugal. This will be a dictionary with all the years and the corresponding values. So in this dictionary we can look at year 2001. So this tells us life expectancy in Portugal in 2001, which we extracted from that Excel file. And we can do this for any country that we kept and any year. Now, to plot the data, we want to draw a circle for each country. We need the X and Y coordinates for some indicators and the size of the circle, some other indicators. For example, we're going to use GDP and life expectancy and population for the size, but we can generalize this and allow it to be anything that we want. As long as they come in as those dictionaries, then also should work. Okay. Now we need some more sophisticated plotting, so I'm going to show you an example of creating a figure, getting the object for the axis so we can manipulate the plot there and then show the results. So let's plot a group of countries on a figure that was already created. We receive here the object where we're going to plot. These are the axes for plotting, which has the plot function there. We receive 3 dictionaries, one for the X values, another for the Y values, and another for the size. And these are the dictionaries for all the countries. Then we have the scale here, so that we can scale the size of the circle, because these values can have very different scales. For example, life expectancy can be 70, but population can be 1 billion, something like that. So we need to rescale things. So we can add this scale as an optional parameter, the year in which we want to plot, and a list of the countries we want to plot there. So this list of countries specifies 2 things. Specifies the name of the country and the color we want to plot it in. So we can provide a table with the countries and the corresponding color for the graph. So this seems a bit complicated, but when you think of things like this, you can build functions that then are more useful because they are more generic. Then you can adapt them to other indicators, other countries, other colors, and so on, and you don't need to go change the function to do that. Okay? So now, for each of the countries here, we will get the first. This is an example here of what we do. So this is the list of countries. In this case, Portugal, and this is red, green, and blue. So we are using green color there. Spain is yellow, which has red, green, and no blue. China, Germany. We send this to the function to specify how we want to represent each country. And now we look through those tuples in that list, and we use the first element here, which is the name of the country, to get the data for that country. Then we go find the data for the year in that country, and we take from the X will be from this dictionary, the X valve, the Y from the Y valve dictionary, and the size will be transformed. So this is the square root of the value there multiplied by this scale, so we can make it so that the area of the circle is proportional to the value that we have, and we use the scale to adjust the size of the circle so they don't become very large or very small in our graph. And now we're going to plot a circle here. So with a marker is a circle at this value. We fill it with a color. This is the size of the marker. Alpha is the opacity of the shape that you're drawing. So if you use an alpha of 0.5, it's semi-transparent. And then we use as a color this tuple here to specify what's the color of the circle. So with this function, we can just put in all the dictionaries, specify the color, and it will plot for 1 year all the countries that we specify. So here is how we can use that. We import these two functions from our module, from this module that we are writing. We import from matplotlib the pyplot module, and then we load the three indicators into those three dictionaries there. So we get data from life expectancy, GDP per capita, and population. And now we specify which countries we want to plot and what colors. We create a figure. We add the axis. So this is the part where the plotting will occur. You can see this the documentation online for this function, but you can specify the size of the plotting area inside the figure, and you can specify the limits and don't change the scale. So all the scale false is so that when you plot something, it will not automatically change the scale of the axis. If it does that, then the animation becomes strange because the axis will be changing during the animation. So we fix that, and we set the X scale to logarithmic. Now this is to show that you can actually change in detail how the plotting works. In many cases you don't need to do this, because if you want just to plot something, you leave the automatic scale, you don't need logarithmic plots, you just plot as we saw before with the tuberculosis plot. So for most of the time you don't need this detail. But sometimes you need a specific chart with you need to keep the axis the same for all the charts you're doing, or you need logarithmic scale somewhere, so you need a finer control of how the plots are made. And this is not so that you memorize how to do this, but just that you know that you can do that. So look it up on the documentation online or something like that, and you can go into more details and control the plots that you make. So this is just to put the labels on the axis, and now we can draw for 1960 all the countries. So now we can these 4 countries. So now we run our program, and we have an error here. The program starts, and we have this key error 1960 that occurs here. So this key error occurs whenever this occurs, you should really look at what the error message is, where in the code it's occurring, and what type of error occurs. So we know that when looking at this dictionary, which has the gross domestic product, we have a key error for 1960. This means that we are asking for year 1960, and we could not find that in the dictionary. Now we know that for some countries there are missing years in the data, so it's possible that there are some years that are not present in the dictionary because we could not find data and we did not put it there. So this is an expected error. It's going to happen a lot because we have missing data here. So now we need to think about how our program should react when this error occurs. One easy solution is simply not to plot that country if there is no data. So if there is no data, the circle does not appear for that year. So this, we can do it in this way. This is the standard way for handling exceptions in Python. So these errors, syntax errors, you cannot handle because they are really, the interpreter cannot understand the code. So those you really have to fix. But these runtime errors that occur during execution, are called exceptions, and something went wrong. The interpreter knows what you want to do, but it cannot be done because something is missing. For example, the key in the dictionary is missing. So we can create this try except block, which tell the interpreter to try to do this, but if something goes wrong, then do something else. And we can specify, we should always specify what we are expecting to go wrong. So it will try to do this, but if there is a key error exception, don't do anything, just move on. So this means if it tries to plot a country, but it cannot find the data for that country, it will not plot that country and move on to the next. Okay? This is important to specify. You can just do except path, and it will do that on any exception. But exceptions include, for example, trying to break the program or something else going wrong, and those things should stop the program so that you figure out what is going wrong. But if there is a particular exception that you are expecting sometimes to occur and you know how to handle, you can just build it in your program. So if there is, in one of these dictionaries, a key is missing, it will ignore that block and move on to the next country. So this block is inside the for loop, and we'll try to do for each country. Okay, so now we can create a simple function to plot in these axes the three dictionaries, the size, the scale, the countries, and given a list of years. So it just looks through all the years and draws the countries in the same plot. This will draw everything superimposed in the same plot, but it's easy to use. We just set up the plot and then plot everything there. We put the labels for the axis, the logarithmic scale, and so on, the title, and we plot everything there, and we get this result here. So since the circles are semi-transparent, we can see a bit where they overlap, and we have the trajectories for the different countries that we're plotting here. But if we want to do this as an animation, there are some alternatives here. For example, matplotlib has an animation module, but the animation only works while the program is running. So if you want to do that for a presentation, like I did here, it's best to save all the images and then create a GIF, for example, or a video with all the images to show the animation. So this is what I'm going to use here. It's easy to join all the images together in a GIF. For example, with GIMP, you just import everything and save as a GIF. Or you can use a simple editor also to save as MP4 or something like that. So there are lots of tools that can do that easily. So what we're going to do here is to create one image and save it for each year, and do that in a sequence. So basically, we load the data, we look through all the years that someone specified for us to plot. We create a figure with always the same axis and the same scale. So this is important because the axis must not change, only the countries inside the graph. And now we draw the countries using that other function that we created, and we use this savefig function from matplotlib. So this you give a file name with the extension, and it creates the image in the appropriate format. You can do it in PNG, in JPEG, things like that. So you can save the image. You should close the figure because these plots take up memory space, and if you keep them all in memory, it's probably going to overload your memory. So each time we create one, we close it, free the memory, and then create a new one. And I just put here this print because this takes a bit to create. Each one takes a few seconds, so you see the progress there and when the program is finished. So now we run, we specify the countries, and we run this function. We see the output there printing the years as it starts to generate the images. Then we compile everything into this, and this is how I did the GIF. So this is a bit more complicated, but the idea is that you get a feeling for how you can solve even these more messier problems where the files you need to use have some problems in the structure, missing values and different files and so on. You can think of how to gather all this data in memory. For example, we use dictionaries. We're going to see next week the pandas library, which makes it easier to deal with tables, so you can also use that one. But you basically load everything into a format that makes it easier to handle things, and then you go from there and you write the additional functions to do whatever you want. Okay? And this is always also to illustrate plotting, where you have both easy basic plotting. You just put the x and y values and select the color, and you have a plot. Or you can fine-tune it if you have one logarithmic scale and the other not logarithmic, and if you want to draw different things in the same graph and use different sizes and so forth, you have lots of access to the details if you want to, and you can just look up the documentation. So to sum up this part, we saw how to use code from other libraries. Here we use XLRead to read Excel files, CSV to read the CSV files, matplotlib to do the plotting, and also you can use your own code as libraries, because once you start building tools for doing some parts of processing, you can store that in a module. Say you have this set of functions that is already done, tested, and so on. This can be a module that you can now import into other parts of your code and reuse as you need. There's lots of details here, but don't panic right now. At least wait a couple of weeks. No, but this will start to become easier, because the reason for doing this is we really need to get up to a good start so that we can go to the interesting part, which is how to solve real problems using statistics packages and handling tables and producing graphs and so on. So we need to skip quickly over the basics, because otherwise we will only be looking at the basics. But we will be going through this repeatedly. So in all these sessions you're going to do loops, use variables, write functions, and so these things will eventually start to become a lot more natural and a lot easier to work with, and this way we can focus on practical applications. And also from here on, basically today, the basics you need to know to write code, and plotting I think everyone will need to plot charts eventually. But now next week we're going to look at numerical NumPy for handling numerical data, and then pandas for handling mixed data with categories and tables and so on. And here you'll probably all need to focus more on one kind or the other. So if you're dealing with experimental data, for example, from a spectrophotometer or something like that, you will you will probably focus on NumPy, because you have tables of numbers and nothing else. Okay. If you are dealing with categorical data and that kind of thing, then pandas is more useful for that. And then in the last day, I'm just going to talk about some more advanced techniques that you may or may not need. Things like how to fit in your Python script into like a bash script, where you can fit it together with other programs and that kind of thing that maybe are useful or not, and then work on your particular problem. So we're going to shift this to more practical applications starting next week. This part you should try to reach a point where you can look at the code and understand what's happening there. It's not useful to try to memorize everything, because that comes with practice and time, and also you're always working online. So Google, you don't need memory, you have Google. That part is not a problem. You just need to be able to read and understand the code so that you can adapt it to what you want. Okay. So what I suggest is that you practice depending on where you're feeling comfortable. So look at the examples in the lectures. I also provide the code for the lectures in the site, and also the exercises, the tutorials. Especially in the first part, you have lots of tutorials where you don't really need to do anything, just follow the steps. These are good if you're feeling too confused and want to go slower. If those things are too easy, you just skip ahead and do the exercises, or try to write on your own some parts of these that I showed in the lecture. So you have a wide range of difficulty levels for where you feel comfortable. But you should try to practice a bit during the week, and email me if you get stuck somewhere. Okay? You can also read a bit more about the IPython console. There are some useful tricks. For example, you can use the errors to cycle through previous commands. You have those magic commands for plotting online or not. There are some tricks like that you can look up, and they may make it easier to write code eventually. If you're still in the basics, don't worry too much about those things, but as you progress, those things can simplify or make it faster to work with these tools. Okay. So questions?